Okay, so good afternoon and thank you for joining. I am going to get started. Like I said, I don't want to be taking more time when you're already taking some time from your valuable lunch hours to join. So today I want to talk a bit about the brain and how it learns to read. And just so you know, because I have my notes open here, I actually can't see the chat or anything right now either. So if you do have questions, I will definitely make sure to answer them all at the end. Please go ahead and jot them in the chat or just save them yourself and ask me afterwards. I'm definitely able to stay and chat for a bit afterwards. I do want to note that I'm speaking specifically about the brain and how it recognizes and figures out the words that are on a page. So I'm not going to be speaking today about the prerequisite skills such as phonological awareness, other than here in brief, kind of in passing, or the other skills that will also need to be built, such as the language comprehension. So I'm focusing specifically on decoding today. And I am not by any means an expert. I'm just sharing what I've learned and am continuing to learn more about. So studies show that 95% of children can learn to read. And this is what kind of started my journey when I was noticing that there were too many students in my eyes that weren't seeming to grasp reading the way that we were teaching it. So I started wondering why and looking into it further. And that's led me down the journey that I'm on now. Because if you look at this next slide, currently in Saskatchewan, 75% of Saskatchewan's grade 3 students are reading at or above grade level, which is 20% less than what data shows should be in terms of students who should be able to read. We also need to be careful in interpreting that result, because in grade 3, after that age is when students start moving from texts that have a whole lot of pictures in them to texts that don't have as many pictures. And one of the strategies we often tell students is to look at the pictures to help figure out what the words are. So we often will see some students that seem to drop off in their reading abilities after grade 3 because the strategies that we've given them or that they use aren't effective or aren't working for them anymore. So we do have to be careful in interpreting some of the data. That's just a little side note. But even just with that 75%, that's worrisome to me and to many others, because that is 1/4 of our population that is reading below grade level. And as they grow, you can see that gets, with some of the statistics on the bottom of the slide, that can get worse and worse. And those numbers are scary to me. And so, how should we be teaching reading to maximize the potential of all of our students, to make sure that they're all learning how to read? So it's worth taking a bit of our time to check in with the neuroscientists, so those who are studying the brain and the process the brain goes through when learning to read. So that's where we're going to spend our time during this Lunch and Learn, looking at what the science has found about our brains. So the field of neuroscience, which is the study of the nervous system and the brain, has changed dramatically in the last few decades because of new technology that has come out that allows the neuroscientists to study the brain in real time. And this technology is allowing them to watch what our brain does at the moment it encounters or sees that written print, as well as how and what it does to interpret that written print. And this has greatly advanced our understanding of how children learn to read. It's disproven some theories and it's proven others. And what's interesting to me is this last bullet. How the brain learns to read is considered a settled science, which means it's been so well studied that the field of science actually believes they know this is how the brain learns. It's settled. Unfortunately, these findings aren't finding their way or having a hard time finding their way into the education system. There's some sort of disconnect. And some of you may have heard of the science for reading movement. And that is a more recent movement, but it's trying to rectify the fact that all these hundreds of studies that exist about reading, they're trying to get that into the forefront and make sure education is aware. So that's kind of where that science of reading movement is from. They're trying to make sure that the data that we have about reading and how our brains read is a part of how we teach education. So now let's talk about what the brain does when it encounters written print. So what do neuroscientists know? So despite what many of us have learned, reading isn't natural. Speech is spoken language. If you think of primates, different animals, we all have ways of communicating language. That spoken part, that is natural, but reading isn't. And if you think of our classrooms, we often think with our students, if we surround them with books, immerse them in books, are always reading to them, they're naturally going to be able to pick up that language and figure out how to read. But unfortunately, that's not the case. Reading is a relatively new invention with writing, because it coincides with writing. It's only a few thousand years old, and our brains aren't able to evolve that quickly, so they haven't adapted to this new invention. So what many neuroscientists have shown and are starting to figure out is that there's a region of the brain that has been used for something else, and it's being recycled, reused for reading and writing. And this neuronal recycling, this term was coined by Stanislaus Dehaene, who is a leading researcher in neuroscience and how brains learn. And he states that writing is a cultural innovation, and our biology still holds the upper hand because we're recycling a portion of our brain. Our writing and reading systems have developed to within the constraints of what our brain is able to handle. So because our brain understands lines and corners and where things meet well, all of the languages that exist are built around that idea of how our brains can interpret and what it can understand. So it's very interesting to study and understand that reading and writing are taking over a part of our brain that didn't exist before. So here is a diagram from Stanislaus Dehaene's book. Now, Stanislaus Dehaene, I will explain, he and a couple of the other research I'll talk about in this presentation, they have taken, so Stanislaus Dehaene in particular has taken about 100 years of different information, different studies, different even from theories, and taken all of the information and put it into this book to explain a century's worth of data that has come about based on our brain. So it's a very good read. It's a heavy read, but it's a really, really good one. But what he says, and so this diagram is from his book, based on all the studies that have been done, is that when we first encounter a letter or a letter string, our retina, so our eye, sees it as an image. Our brain then recognizes, oh, this is a letter or a letter string, and transfers the information to the exact same spot in every brain, regardless of the language it's in. And this part of the brain has been termed the visual word form area. In short, we often call it the brain's letterbox. And in the diagram, you can see that's that little red area. And this is a diagram of the brain from below. So this is in our left hemisphere. Kind of, I think, in behind the ear is roughly where it is. And then it's sandwiched in between that little yellow box, which shows that's our area that recognizes objects. The green area is the one that recognizes faces, and then the blue is the one that recognizes places. So our recognition of the letters is right in that visual area. And that's the part that's being recycled. So when that image gets to the letterbox, that letterbox then recognizes what the letter strings of letters are. The letterbox then sends that information to different parts of the brain to process the sound that visual letter represents and the meaning of a string of letters, among other things. So this is important to know. The letterbox just stores the visual image of those letters or those letter strings. It doesn't store the sound or the meaning. That's different parts of the brain. And if you look at the last bullet here, those different parts of the brain, so if you look at the dots on the diagram in green and orange, those are areas that connect to the sound and the meaning of words. Now, these areas already existed in our brain because they're connected to spoken language, which is a part of is a part of what our brain is set up for. But the letterbox then connects and sends out information to these areas to help us. So these areas are necessary for us to be able to read, but they're not connected specifically to reading. They're connected to our spoken language. So our brain needs multiple exposures to letters and letter strings to build an information superhighway. So the synapses and the neurons, they need to become very strong connections, and the stronger connections come through repeated multiple exposures. The stronger their connections are, the more efficient our reading becomes, the more quickly and accurately we connect to sound and meaning when we see letters and letter strings. Once we have learned a letter or letter string through multiple exposures, it's stored in that letterbox, that visual word form area, to be quickly retrieved when it's seen again. And that is now, that letter or letter string is now considered orthographically mapped, and we'll talk about that in a little bit. Neurotypical students, so our students that seem to be doing quite well with reading and pick it up easily, normally only need a few exposures to a letter. A couple of the different webinars and books I've read kind of talk of anywhere between 4 to 14-ish. So not an exact, but about that amount of exposures to recall automatically the sound as soon as they see that letter. Those with reading difficulties can need anywhere from 40 to 400 exposures before that letter sound connection is orthographically mapped, so it becomes learned and automatic. So you can think in our school day, those that need those extra exposures need a lot more time. So the more exposures we give, the more chance we have of those students picking those letter and letter sound connections up more quickly. So this is Stanislaus Dehaene, and a quote from his book that I will read to you. Or sorry, I'll just explain to you quickly, but he basically says that we don't know exactly when our brain reaches its adult arrangement. So it's in terms of letter recognition, when it kind of finishes forming. But what we do know is that around the age of 5 or 6, that's when the visual recognition process is in place. That's when it has the most plasticity, so the most ability to change. So this period is very, very important and a very good time for the acquisition of visual shapes like letters and words. So you can see even our education system has already kind of figured that out. That's when kids are starting to read. That's when their brains are very open and able to learn. So now let's go to that orthographic mapping piece and explain a little bit more about that. So Stanislaus Dehaene talks about 3 major phases in terms of reading acquisition. Now, a lot of studies, some talk about 3 and there are a bunch that talk about 4, but they all kind of cover the same information. So I was just thinking, I thought I would stick with Stanislaus Dehaene's explanation because I have been quoting a lot of his work already. But he talks about 3 major phases. The first being the pictorial stage. This is the first stage children go through when learning how to read. And this is kind of a brief period of time where kids photograph words. So they might see like a Coca-Cola can. They don't know all the sounds of those letters, but they recognize the image of those words as being, oh, that's Coca-Cola. So they recognize the image of it. And then they move into the phonological stage when they're learning to decode. So they're looking at graphemes or written letters, and they're decoding them and figuring out what their phonemes, their sounds are. And then finally, they move to the orthographic stage, and this is where word recognition becomes fast and automatic. So brain imaging shows that several circuits are altered during this process. So basically, the biggest things they notice in the brain, the biggest part that changes is that letterbox area, as well as kind of that information superhighway between different areas of the brain to connect sound and meaning to those letters and letter strings. So in essence, we're moving from phonetic letter by letter decoding to recognizing strings of letters together when we've been exposed to these strings of letters enough. So we orthographically map these letter strings. We quickly and almost instantly recognize those letters and their pronunciation when we encounter that letter string. And then these are stored in our letterbox. And then David Kilpatrick, another researcher I mentioned very briefly earlier, he's another doctor, I believe, as well, who has looked at all the different research that exists. And he looks specifically mostly at orthographic mapping and phonological awareness. And what he says, he follows behind what Stanislaus Dehaene, and they agree with a lot of what they're writing. So he says the word's pronunciation is already in our long-term memory, or it's quickly put there. When students learn new words, they quickly learn the spoken representation of that word. But mapping helps the printed letter string anchor to that pronunciation in the long-term memory, making it familiar. And after a few exposures, the word is mapped, so it's now a familiar letter string. And seeing that familiar letter string instantly activates the word's pronunciation. And I'm going to read this quote directly to you because there is so much really good information in here. So this is from Stanislaus Dehaene again. So he says, at this stage, the orthographic stage, reading time is no longer determined primarily by word length or by grapheme, which is the letter, complexity. Rather, it becomes increasingly influenced by how often a word has been encountered. So rare words are read more slowly than frequent ones. The number of neighbors also emerges as a major factor. So a word like vein, which is surrounded by high frequency neighbors, such as rain or pain, is read more slowly because they haven't been exposed as frequently to that word. All of these effects reflect a gradual establishment of the second reading pathway, which is the lexical route, which progressively supplements letter to sound decoding. Probably the clearest feature of the orthographic stage is that word length gradually ceases to play a role. At the phonological stage, children slowly decipher words sequentially, one letter at a time. As a result, reading time increases with the number of letters in a word. So again, a longer word is going to take longer to read. At the orthographic stage, however, as reading becomes increasingly fluent, this length effect slowly vanishes. It's essentially absent in expert adults. we all read words using a parallel procedure, which I'll explain about in the next slide, that takes in all the letters at once, at least in short words, 8 letters or fewer. So basically, any word with 8 or fewer letters, if it's 3 letters and 8 letters, we read it in the same amount of time because our brain looks at all those letters at the exact same time. So we are able to read those words very efficiently, and again, in the same amount of time, even though they're much shorter versus a bit longer. So this neuronal analysis can now be effortlessly, there we go, transmitted in parallel to brain regions that compute meaning and pronunciation. So again, once we figured out that letter string, and it might be an automatic thing, we also very quickly reach out to the other areas of our brain to figure out what it means and how to pronounce it. So now that parallel processing that I just mentioned. So parallel reading, how do we read words? Reading has become so automatic for adults that we've forgotten how we learn to read. And due to how quickly we can read words, we, for the most part, assume that our brain reads by looking at a full word. We look at the whole word and not by looking at each individual letter. However, for what I read just on the other slide, you might already have figured out that science has disproven this. Our brain actually sees every letter in a word, even once it's been orthographically mapped. We just see it in parallel. It's called parallel processing. So it notices each letter and processes the letters simultaneously, all at once. We're just so quickly able to retrieve that word from the letters the brain has recognized that we assume we've noticed the whole word and not the individual letters. And this quote from Kilpatrick, if we did not attend to every letter of the words we read, we could not instantly recognize words that differ from one another by only one letter. And when I first read this, I had some aha moments, but then I automatically thought of those little pictures you can often see online where they have the words where only the first and the last letter are the same, and all the letters in the middle of that word are jumbled up. And we all interpret that to mean that we can read without actually looking at all the letters. But what it actually means, and Stanislaus Dehaene explains this a bit in his book in more depth as well, is our brain is able to look at all those letters at the exact same time and know, oh, those letters are H-O-U-S-E, even if the middle letters are mixed up, and it knows that's house because of the individual letters, and it's matched it up. So we still aren't actually looking at the whole word. We're looking at every single letter in that word. So then a thought to ponder based on this parallel reading and parallel processing is, how are we as educators teaching to whole words, believing this is how our brain learns to read them? And knowing what the science knows, this actually is inefficient because our brains don't actually learn it that way. So we're using valuable educational time using a strategy that isn't actually what our brain needs in order to be able to learn how to read. Now, I did want to make a note that there are some words that are completely irregular and can't be decoded phonetically or by using syllables or morphology. These words will still need to be taught as whole words. However, the percentage of words that are actually irregular in the English language is about 4%. So for the whole English language, we're used to often saying, and I've said it myself many times before I knew all of this, English is crazy. It doesn't make sense. You just have to memorize it. But that actually isn't true when only 4% of our words are actually irregular. Once you know the history behind the words, the etymology, the morphology, as well as syllables, and all the different ways we spell certain sounds based on the history of those words and those sounds. So this is, if we empower kids with this information, we can get so much further in their reading abilities. So based on this information I've just shared, scientists know now that reading needs to be learned through explicit teaching of phonics, the sound and symbol correspondence. I also picked a couple other key findings that I wanted to share with you this afternoon, just as something that you could take back with you, put in your back pocket and know, and I thought it was really valuable for educators to know. So first is the idea of object invariance. So in a quote from the book, again, from Stanislaus Dehaene, he writes, reading poses a difficult perceptual problem. We must identify words regardless of how they appear, whether in print or handwritten, in upper or lowercase, and regardless of their size. This is what psychologists call the invariance problem. We need to recognize which aspect of a word doesn't vary, so the sequence of the letters, in spite of the 1,001 possible shapes that the actual characters can take on. So when I was thinking about this too, I'm like, this is very logical. With all the fonts we have out there, words can look so different. And our brain needs to recognize, no matter what font it is, what size it is, what that word is. So scientists have found three kind of key findings. First, our brains don't look at the location of a word on a page. No matter where on a page it is, it can figure out what it is. Our brain also corrects for the immense variety of ways a word can look. So if you look at the picture to the side, the different sizes, the different fonts, it can even correct for slight errors within the words because it knows letters that look like those letters, and it can make a correction. Oh, that E should have been a C. So it actually corrects for some of those errors. And word recognition, and this was one that really stood out to me, this last bullet here, is that it's mostly invariant for character shape. So studies have proven that our brain doesn't actually pay attention to the shape of a word. So here's a quote again. If we can immediately recognize the identity of words in lowercase, words in uppercase, and words in mixed case, it's because our visual system pays no attention to the contours of words or to the pattern of ascending and descending letters. It's only interested in the letters that are contained within that word. So obviously our capacity to recognize words does not depend on being able to analyze their overall shape. Now this was mind-blowing to me because I, like many other teachers, we aren't necessarily trained to understand and know all of this. So that thought to ponder, I did these words like this myself, not realizing and not understanding the brain science that this is actually a bit of an inefficient use of our time. Again, because our brain, it's proven that our brain doesn't actually pay attention to word shape. And then one more thing here that I wanted to go over was letter reversals. I know this is a common topic, especially in early years classrooms. So if we circle back to the brain's letterbox and that it's being recycled, that letterbox area is being recycled for reading. It's in the visual part of our brain. To understand why reversals happen, we kind of need to go way, way back to our days as cavemen. Generalization and invariance during that time of our life was incredibly important. If you think about the visual part of our brain, it needed to recognize a problem from any angle. So we needed to know if there was a tiger coming to attack us, we needed to recognize that was a tiger if it came at us from the left or the right, because we needed to have time to react. So we needed to immediately know that's a tiger, no matter what angle it came at us from. So our brain uses generalization and invariance. A tiger is a tiger from any angle. The implication now is that this is the same part of our brain that's being recycled to recognize letters. So it has to unlearn that tiger is a tiger from any angle. It now needs to learn that a letter isn't the same letter from any angle. So think again, that B, D, P, Q, all the angles, our brain initially sees all of that as one letter. So we have to unlearn that. And this is the reason why so many students struggle with letter reversals. So it is very typical. Letter reversals happen to all of us. At the beginning, we all have to unlearn this. Normally, repeated exposure and practice with these letters will take care of this, and children will naturally outgrow it. Most do, but there are some that don't, and that's a different topic altogether. So overall, to learn to read English, the child must figure out the relationship between sounds and letters. So the beginning reader must learn the connections between the approximately 44 sounds, and I say approximately, and they do as well, because with different dialects, different accents, some areas have a few less phonemes and some have a few more. So we need to figure out the connections between those phonemes, the spoken English, and the 26 letters of the alphabet, and the multiple ways we combine those letters to make the different sounds. And Stanislas Dehaene says, we know now that the whole language approach, so whole word type approach, is inefficient. All children, regardless of their socioeconomic backgrounds, benefit from explicit and early teaching of the correspondence between letters and speech sounds. So a few simple truths should be accepted by all. In spite of variations in the speed at which we learn, all children have similar brains. Their cerebral circuits are well tuned to systematic grapheme, phoneme, letter sound, correspondences, and have everything to gain from phonics, the only method that will give them the freedom to read any text. And so in conclusion, I raced through all of that information, but I did want to say, if you're interested in learning more and about possibly implementing some practices in your school or classroom based on the scientific research of how brains learn to read, and that decoding specific, like this presentation was, or in other areas of reading, we would love to work with you. You can please feel free to contact myself or any of the other early years literacy coaches directly through email or by filling in our request form through this QR code, and I can always send that to you if you'd like later. Just let me know. And I would also love to ask if you could scan this code and provide us with some feedback on this session in terms of what you've learned and what you're taking away from it. That would be much appreciated. And lastly, I will stop the recording here and I will take some questions. I will stay on if you guys have some questions or would like to go over anything with me. Thank you very much for joining.